Okay, so now we're going to talk about section 2.2, which is it talks more, it goes into more detail about limits. We did look at limits a little bit in the last unit, right? We were looking at the average velocities, and when the endpoints get closer to each other, what does the secant, the values of the secant or the averages approach? So before we start, there's an acronym that you see in here a lot, DNE, and that stands for does not exist. Okay, and so what we're going to do is, if you haven't seen this notation before, you're seeing it now. We want to find the limit of f of x as x approaches a, and and let's say that number is some double value or real number L, and so we're going to learn how to calculate L. And there's a couple ways we can do it. So for the most part, it says we can use algebraic techniques to determine the limit. We'll use that, or maybe even just some rules for taking derivatives. There, you can graph it and then kind of just get an idea. It's not very useful to me. Get an idea of what the slope or what the limit is as x gets really approaches a, what is the value of f of x, and numerically. So basically you just draw a table of points really very close to a and see if they're establishing some kind of pattern. And we see that in example 1. Okay, so this is a difference quotient, and the numerator is f of x squared. It's that polynomial x squared minus 5x plus 6 divided by the binomial x minus 3. Okay, and then what is the limit of that quotient as x gets really close to 3? So, our immediate reaction might be, oh, well, it's infinity because we're dividing by 0, but that's actually not the case. Okay, so we just measure values very close to x equal to 3, like 2.9, 2.99, let's say 3.01 and 3.1. And the closer we get to x equal to 3, we see that the limit or the value of f looks like it's getting close to 1. Right, so again, we're looking at that difference quotient, x squared minus 5x plus 6 divided by x minus 3. And what is the value of the function when x is really close to 0? And it looks like when x is 2.99, the function is 0.99. When x is 3.01, the function is 1.01. So, maybe a good guess for x near 3 is the limit is actually equal to 1. Because you can't just plug x, because the problem is we can't just plug x equal to 3 in there because the denominator will be 0. We can't divide by 0. Okay, so there's graphically, so if you can see that graph on the bottom of page 1, okay, so it's a straight line, except it looks like there's a hole in it at x equal to 3. So if we approach, let's say we approach 3 from the left, starting from like the origin, going towards 3. Okay, it looks like it's, the value is going to be 1. And okay, and so then let's say you approach 3 from the right, again, f of x is equal to 1. The one thing we can see is that f of 3 does not exist, that DNE, see, f of 3 does not exist. See, there's a hole there. So the function the function is defined everywhere except x equal to 3. And that's where the hole is. But again, if you just look at numerically, it sure looks like the limit of x squared plus 5 minus 5x plus 6 over x minus 3. It looks like the limit is going to be 1. Yeah, the limit's going to be 1. Okay, just double checking there. Okay, even though the limit is 1 as x gets close to 3, but f of 3 does not exist. But if you're on if you're on either side of 3, really super close, the value of the function is about 1. Okay, there's something called one-sided limits, which we use sometimes in this course. Okay, that's what if you're approaching, it's like in this previous example I showed you. We approach x equal to 3 from the left, and that's, we're going from 0.9 to 99. And we approach it going from the right, we're going 1.1, 1.01. In either case, we saw the limit is about 1. that the function gets close to 1. Okay, now we can look at limits. Okay, let's say let's say the limit of f of x as x approaches a from the right. So we look at values of x very close to a, but only it's bigger than a. And then there's also, we can evaluate the limit coming from the left, and that's for x less than n. So when x is really, when a is really close to x on the left, that's the limit as we approach, yeah. So if we want to find the limit as x goes to a from the left, so we look at values of f of x near a but less than a. If we want to look at the limit of x of f of x as x approaches a from the right, we look at values of f of x close to a, but only in this case x is bigger than a. Okay, so let's just look at, so there's your definition, okay? And so those two limits as you're going from the left and going from the right might be different. Okay, so now let's just look at this function in example 2, and there you will see a difference. It's the absolute value of x minus 2 all over x minus 2. Okay, and so for x positive, let's say x is greater than 0, like x is 3 or 4, any positive number greater than 2, that the absolute value of x minus 2 over x minus 2 is going to be 1. So the function is equal to 1 for x greater than 2. And the function is actually negative 1 because the absolute value of still for x, for negative x. Okay, so in x minus 2, the quantity x minus 2 is negative. We get that the absolute value of x minus 2 is minus the quantity x minus 2. Okay, so let's just look at, and the graph is actually that step function, right? And if you see where it says jump, okay, so as we get very close to 2, the value of the function is negative 1. So for x is less than 2, it's, so let's say like 0, yes, or so then the absolute value would be, so let's say x is 0. Okay, let's say x is 0. We know the absolute value of 0 minus 2 is 2, but so the absolute value of 0 minus 2 is 2, but 0 minus 2 alone is just negative 2. So that quotient is actually equal to negative 1 for x less than 2. And I'm looking at the function absolute value of x minus 2 over x minus 2. And the quotient is 1 for x greater than 2. So for x less than 2, x minus 2 is negative. And for x greater than 2, x minus 2 is positive. So once again, the value of the function is a negative 1 for x less than 2 and positive 1 for x greater than 2. Okay, so now what is the limit of that function as we get close to 2? Well, it's going to depend on which side you come from. So if we're approaching 2 from the left for values of x less than 2, the limit is 1. As you go really very close to 2 for values of x less than 2, just look at the graph. The value of f of x is negative 1. Now, if we approach 2 from the right for values of x greater than 2, right, the value of f of x is equal to positive 2. So the limit coming from the left and the limit coming from the right as x goes towards 2 is different. So from the left it's negative 1 and from the right it's positive 1. So the limit, let's say, so the limit as x goes to 2 of f of x in this case does not exist. Okay, because what we're eventually going to see is that the limit coming from the left, and so if the limit at x equals 2 exists, that would mean that the limit coming from the left and the limit coming from the right would be the same thing. Okay, so here's another piecewise example in example 3. And once again, we see that the limit coming from the left is different than the limit coming from the right. So as we approach, and let's just look at that function f of x as x goes to 0. So f of x is equal to 3 for x positive, and f of x is the downward sloping line minus 2x for x negative. Okay, so as x goes, let's say goes towards 2. Well, 2 is greater than 0. So the answer, and the function is defined to be 3. So that's pretty easy, I guess. Okay, and so now, let's say the value of, let's say x is going to negative 3. It's a little smaller, but I think that's the limit as x goes to negative 3. You plug in negative 3, negative 2 times negative 3 is 6. So in that case, we can just do direct substitution. right? So we're not near a point. We're not going towards a point where there might be a jump in the graph, or there might be a hole missing in the graph. But when you look at the limit as x goes to 0, okay, so if we approach 0 from the right, the limit is 3, right? Because it's actually just the line y equal to 3. And if we approach f of x as x goes to 0 from the left, in this case, you can see that and the function is actually defined at x equal to 0. In this case, so if we approach 0 from the left, the value of f of x is 0. So the limit going to from the left and the limit coming from the right are two different values. Okay, so in this case, let's look at example 4 here. We can't use direct substitution here. So in this case, let's let the function be f of x for all values of x not equal to 1. F of x equals x. The slope of 45 degrees. Okay, but at x equal to 1, we'll say f of x is equal to 3. So as we approach x from the right, f of x goes towards 1. If we approach x from the left, if we approach the limit of x, as x goes to 1 from the left, f of x is 1. As x goes to 1 from the right, f of x is 1. So I think it's fair to say that but what it turns out is that f of 1 is actually equal to 3. And it turns out the limit as x goes to 1 from either direction is 1. So the limit as x goes to 1 is actually equal to f of x is 1, but it turns out f of 1 is 3, right? So if you are near 1 on the right or the left, it's really like 1.01 or 0.99 or 0.99999 or 1.000001. When you're really close to you're taking values of x super close to 1, the value of the function is getting pretty close to 1 on either side. So we can say that the limit as x goes to 1 of f of x is 1, even though f of 1 itself is equal to 3. It turns out just because the function is not continuous, right? To graph it, you have to take your pencil off the paper. That's my definition of continuous. And you have to take your hand off the paper. Okay. So now we won't look at all of these, but let's look at, okay, there you got that piecewise function again. And it's discontinuous at x equal to 1, right? So when you draw this graph, if let's say you're drawing it from left to right, when you got really close to 1, you'd have to lift your pencil off the paper, right? So the limit as x goes to 1 from the right is 1, right? So if you look at values of x like 1.001, 1.00001, okay, the value of f is getting really pretty close to 1. And if you approach x from the left, values of x a little bit less than 1, like 0.99 or 0.99999, we see that f of x approaches 2. Okay, so the limit as x goes to 1 does not exist. Okay, because we get different values as we approach from the left and from the right. So for the limit to exist, the limit coming from the right has to be equal to the limit coming from the left. So well, here we see another one in example 6. You take the limit of that's called the hyperbola. We're graphing 1 over x. And if you take the limit as x goes to 0 of f of x, well, the limit does, you don't even get close to 0. As you approach from the right, the graph goes to positive infinity. And as we approach x equals 0 from the left, the graph goes down to negative infinity. So the limit of that hyperbola, f of x equals 1 over x, as x goes to 0 does not exist. Okay, and I think that's all we'll say let's just look at a few more here. We don't have to look at exactly everything in here. Okay, so the limit of, this is kind of interesting, example 8. Okay, this is pretty straightforward. If you graph the cosine function, as x gets close to 0, the graph of cosine gets close to 1, right? Because cosine, in this case, it's a continuous function, meaning you can graph it by cosine of x without lifting your pencil off the paper. And we know that cosine of 0 is 1. Cosine of 1 over theta, well, first of all, as theta gets closer to 0, 1 over theta, isn't defined. You just kind of get this wild answer for a limit of 1 over theta. Okay, so another one that might be kind of interesting is C. the limit of sine of x over x, so it turns out it's gonna be 1. And so one thing is you can graph the function. Of course, the function's not defined at x equal to 0 because we would be dividing by 0. Okay, so let's just look at value. So if we graph it, we use a graphing calculator, you'll see we have a graph where there's kind of a hole at x equal to 0. So, and that's it. And so we'll learn more about this later on. There's something called L'Hopital's rule. We'll learn to evaluate a sine of x over x that way. And we'll talk about we'll talk about derivatives when we're talking about piecewise functions. But again, so this is a kind of a good introduction to the concept of limits.